Hello and welcome to today's tutorial on quantum. I want to begin by just very briefly summarising what we did in the last class, and I want to do so with a view to getting you to attack the arguments, right? You should never take anything that I say, you should never believe it unless you can prove to yourself that you believe it through a chain of logic. So what I want to do is to summarise in broad brush terms the essential backbone of today's lecture, and then I'm going to ask you to shoot it down, to give examples of how you could question the conclusions drawn. So we began with the idea of classical orbital angular momentum, that if you have a particle at position r with momentum p, then this is its classical orbital angular momentum. Quantum mechanically, we can replace momentum with an operator, as you do. And so the three Cartesian components, Lx, Ly, and Lz, of this equation have the form given in class. And this is again orbital angular momentum. You can then prove. So again, I'm giving you here a chain of logic that summarises a large part of the previous class. But I want you to be staring at this thinking, how can I shoot this down? Where are the gaps in the logic? Where are the logical leaps that you can question? Yep. You can prove, when you do the algebra, that the Cartesian components of this orbital angular momentum operator, because P is now minus IH cross grad, L is now an operator. Instead of P, I have I, H cross with a minus sign, grad. And the Cartesian components of this you can show. And you do the algebra, trust me, you'll get the answer. Or don't trust me, do it yourself, you'll get this answer. You get these formulas, this Lie algebra. X, Y, Z. Cyclic permutation, yep. If I replace X with Y, Y with Z, Z with X, and then do it again, Y becomes Z, Z becomes X, X becomes Y. You get this algebra. We then say that these relations were obtained for orbital angular momentum. But if we replace the L's with the J's, and these operators are Hermitian, as they must be for quantum mechanics, we then said, suppose I give you any set of three operators, any set of three linear Hermitian operators in quantum, Jx, Jy, and Jz. We're now making a transition, we're generalising from this algebra for orbital angular momentum, now for general angular momentum. We say that if you have Hermitian operators, Jx, Jy, and Jz, that obey precisely this Lie algebra, with the L's replaced with J's. And I'm going to write them out because we'll need them for today's class. X becomes Y, Y becomes Z, Z becomes X, Y becomes Z, Z, X, X becomes Y. By the way, if I make any mistakes on this board, please let me know because we'll need to work from this later. So the claim is that any set of three linear Hermitian operators that obeys this is an angular momentum. And so this forms the basis of the general theory of angular momentum. We then prove, using a series of algebraic steps, so we had our generalised spherical harmonics because, and you can show from this, because J squared commutes with Jx, Jy, and Jz, but they don't commute with each other, that you can have simultaneous eigenfunctions or simultaneous eigenkets of both J squared and Jz. And these are our generalised spherical harmonics. Function acts on operator acts on eigenket to give eigenvalue times the ket back again. Similarly for the second equation. We give the eigenvalue a name. Here we called it j plus 1 h cross squared. Here we called it m h cross. J was the general angular momentum quantum number. M was the magnetic quantum number. You then show, using a chain of logic, that the only allowed values for J are 0, half, 1, 3 halves, etc. You then say this is a general theory of angular momentum. Spin, namely the angular momentum that a particle has when it's at rest, is an example of orbital angular momentum. Hence, this result, which follows from an algebraic argument, flowing from what's on the board and nothing else, implies that all spins of all material particles are integral or half integral. More precisely, it's 0, half, 1, 3 halves, etc. Therefore, every fundamental particle has a spin angular momentum, special case of general angular momentum that obeys this. So no particle that exists in the world, no particle can have spins other than this. So that's the argument. We started off with a harmless equation of classical mechanics for orbital angular momentum, and we ended up with a deduction that every material particle in the universe has a spin that's either integer or half integer. Who'd like to stare at this chain of argument and ask the question, I don't believe that jump, and here's why I don't believe that jump, and this will start a discussion. Who'd like to begin by questioning something that's on this board? I'm happy to shoot bullets at my own argument, or at Dirac's own argument, but I'd much rather that you did.
Well, you've claimed that J is 0, half, 1, 3 on 2, etc. Well, why have you chosen those values?
Sorry, can you say that again, please?
Yeah, you've chosen the J values. Yes. Why those values?
Oh, sorry, so you can actually prove this. This can be proved and will be proved using an algebraic argument in the next class. So the question is, why have I chosen these particular values? The answer is I haven't chosen them. I've actually calculated that the allowed little j values are this, using an algebraic argument that we'll get in the next lecture. So for now, could we provisionally assume that, or believe that this is a logical deduction? These are the statement or the claim that these are the only allowed values of little j is a logical deduction, a correct logical deduction, a logically correct deduction derived from what are the other stuff on the board. So this is part of the process of science, right? If we just digress for a second, I make the statement that you make some claim, you give some attempt to justify that claim, and then immediately part of the process of science is to begin questioning, to ask, how can I shoot this argument down? Can someone elaborate on those comments just regarding the general scientific method? I make some claim, I try and give some evidence-based argument. In this case, this is theoretical physics as opposed to experimental. And then immediately you say, how can I shoot that down as a matter of course, as part of the scientific method? Who'd like to elaborate on that?
You find like a counter argument or something that sort of it can't show, and then have an alternate theory that can show it as the previous one.
Yeah.
Answers it all.
So you search for a counter argument.
Or you search for sort of like a hole in the theory.
Yeah.
You find a theory that can explain that hole plus the original theory.
Yes, absolutely. You find a theory that can explain that hole. You seek for the hole in the argument. Then you find a theory that can explain that hole. Can you give an example, a concrete example?
Quantum mechanics in general.
Yeah.
Explain that boils down to classical mechanics, and also explains the weird stuff. Zoom in right.
Yeah, beautiful. So quantum mechanics itself is an example where you have the set of phenomena such as X and Y that can be described by a quantum theory, and that's a superset of phenomena such as Z, which can be described by classical theory. Excellent. Can someone else elaborate on this idea that as soon as someone tries to give you a theory, and it could be a physics theory, it could be a mathematics theory, it could be a chemistry theory, the first thing you start to do as soon as it's presented is you ask, how can I shoot that down? Why is that an important part of a scientific method? So please either answer the question or say it's a stupid question because. Yep.
If we don't ask the questions, we might end up with something that goes down a complete wrong path.
Yeah, if we don't ask those questions, we might end up with something that goes down the wrong path, absolutely.
General case, so you might be able to describe everything in the system instead of just a specific part of it.
Yeah. Can you elaborate on that statement about this being a general case?
So you sort of want everything to boil down to a general case so it can describe every sort of phenomenon, so you're not sort of left in the dark when you're trying to describe certain things.
Yeah, beautiful. Also, when you're doing research, by the way, as you do, and I mean research in the general sense of the term, not just ivory tower university working on some abstract problem, but also research in the broader sense of trying to work out an answer to a question that no one yet knows the answer to, whether you're doing management consulting or theoretical physics. When you're doing research, you're wrong more often than you're right. For every time that I write up something on the whiteboard in my office when discussing with colleagues, trying to find some answer to some question, for every right chain of argument I give, I'll give 10 wrong chains of argument. And that's no exaggeration, because you're groping in the dark, you don't know what the hell you're doing. You're just trying things, you're following up hunches, you're putting things on the board, you're making mistakes. And I'll put something on the board and someone will get up and say, you're wrong because. And then I'll try something else and I'll say, you're wrong because. And then repeat that 10 times. And then when they can't shoot down your argument anymore, then you know that you're on a good thing. So this just gives context to my question when I ask you to throw darts at this argument and to ask what leaps of logic that you don't believe. So let's come back to this, and if I could ask the question again, and I promise I won't ask it, could I just ask it one more time? Does anyone want to have a go at throwing darts at any aspect of this argument?
I know you said J is a general angular or orbital angular momentum.
Yeah.
But how can you immediately make the jump from J to S?
Yeah, so the statement is that I made the claim that J is a general orbital angular momentum, and you asked the question, how do I justify the jump from J to S? Can someone answer this? Yep.
Is J a sum of the spin angular momentum and the L version of the angular momentum, so it's just J equals L plus S?
Yeah, so the question is J a sum of the orbital angular momentum in the spin? And the answer is yes. If you have, for example, an electron orbiting a nucleus, then there's two angular momenta. There's orbital angular momentum, plus there's the intrinsic spin angular momentum. And so you could view, for that particular case, J as L plus S. But the question is, how do I justify this special case?
Are you justifying just the fact that J has half integer values? Is that what you're justifying there?
Actually, again, could I bounce it back to the class? What are we actually justifying here?
The direct transition from J to S.
Yep, the direct transition from J to S. I mean, can someone give me a counter argument? Because the way this works, right, is you say, how can I shoot that down? And so there's a whole lot of links in the argument, right? I start off with this, I go to this, I go to this. And the way that you attempt to shoot down any argument that has a link where you go from one statement to the next, to the next, to the next, is you question every single link, right? I claim that you can go from X to Y. How do I shoot that down? I claim that you go from Y to Z. How do you shoot that down? I claim that you go from Z to W. How do you shoot that down? So every single link can be questioned and should be questioned and must be questioned. Hence the question, how do I justify this? So let me ask the negative question. How could I argue against this? Tell me why, give me a reason why you don't believe this, this jump. I know I'm sort of twisting your question a bit, but let's run with it. question every single possible link. What's an argument that could be given against this transition from general angular momentum to spin? Cool. I don't want to keep pushing it. Have a think about it. But you see the key point that I'm making. It's very, very important to ask these questions, and it's absolutely intrinsic to research. Sorry that question flopped a little bit. I actually want to push my luck. Let's push my luck a bit. Let's talk about electrons. I want to make two statements regarding electrons. Well, let me make one statement regarding an electron. An electron is a fundamental particle of physics. Now, sure, when you have a probability density associated with some electron, for example, in a hydrogen atom, it's smeared out through space. But when you make the measurement, you get a ping on your detector. Yep. So if you were to have, for example, a digital camera, just like you have in your mobile phones, except this is a digital camera that can sense electrons, then you make a digital camera that can sense electrons. You choose whatever pixel size you want, the physical dimensions. The length and the width of these pixels is whatever the smallest you can make. And when you detect you have an electron field shining on this camera, electron microscope, you zap electrons through a sample, they flood through space, and they strike a detector. There's some probability density, but when you measure an electron, it goes ping, and it goes ping here. And the smaller your pixels, you'll just get one particular pixel going ping when you detect one electron. So the idea here is that even though you have smeared out probability density, when you take a measurement, you measure one electron somewhere. So therefore the electron is a structureless point particle. So when the Earth, for example, rotates about its axis, we can speak of its angular momentum. You're in the rest frame of the Earth and it's sitting there rotating, and this is like what spin is. It's spinning. It has angular momentum even though its centre of mass is stationary. But an electron is a structureless point particle. When you bring an electron to rest, it still has angular momentum, but because it's a structureless point particle, that's not associated with any rotation. Therefore, spin angular momentum, the angular momentum electron has when you're it's at rest relative to you, its centre of mass is at rest, has no physical analogue. Therefore, spin is a purely quantum mechanical phenomenon. So there's a chain of argument. Electrons are not extended in space. They're structureless point particles. They're fundamental particles. Therefore, any angular momentum they have when their centre of mass is at rest relative to you is not associated with swirling in space, as it is for the spinning Earth or a spinning sphere. Hence, spin angular momentum, the angular momentum an electron has when it's at rest or its centre of mass is at rest, that has no classical analogue. There's a chain of argument. Does someone want to have a go at shooting down that chain of argument, which begins with a structureless point particle and ends with the conclusion that the idea of quantum mechanical spin has no classical analogue?
I don't know if it's a shooting down, but what's the, you know, if this spin exists, how does it manifest itself physically?
So the question is, if spin exists, how does it manifest itself physically? If spin exists, how does it manifest itself physically? Can someone give us an example of how spin manifests itself physically?
It lets electrons be in the same, like with the Pauli exclusion principle, it lets them be in the same order pair.
Yep. So the Pauli exclusion principle is an example of a manifestation of spin. Pauli exclusion principle means that two electrons, for example, can't be in the same quantum state. If you have a particular energy level, you can have a spin-up electron and a spin-down electron. So the Pauli exclusion principle is one example of a manifestation of spin. Another one is the Stern-Gerlach experiment, when you send electrons through an inhomogeneous electric field, a magnetic field that varies with position. So here's a region where the magnetic field varies with space. You send an electron beam through, it actually gets split. If you look at your film here, you actually get two two imprints on your film for this electron beam passing through an inhomogeneous electric field, it actually magnetic field. It separates out the two spins, and this Stern-Gerlach experiment, to my knowledge, is one of the most direct manifestations of spin. In fact, it was one of the experimental results that prompted this idea of spin. But does someone want to shoot down this idea? Structureless point particles can't swirl in physical space. Hence, when a structureless point particle, such as an electron, has spin, this must have no quantum analogue because it's not swirling in space.
Just thinking about not necessarily structures, but the point particle part of it. I mean, I think a point particle is like an infinitesimal, small thing, but we know that, say, an atom is only automatic strong, then a proton might be 10 to the 15 or something meters, sure, an electron is roughly 10 to minus 15, 10 to minus 20 meters or something in size. So can you really claim that it's a point particle?
Yeah, can we really claim it's a point particle? I mean, 0 is small, right? 10 to the minus 10 of a metre is the size of an atom. 10 to the minus 12 of a metre is 100 times smaller than an atom. But 0 is infinitely smaller than 10 to the minus 12. It's infinitely smaller than 10 to the minus 50. 0 is infinitely smaller than 10 to the minus 1,000. Is it really, when I say structureless point particle, what do I really mean? Do I really mean that it's 0 size? Does someone want to run with that?
Say that its size is negligible, so that would be why it would be able to spin, because it doesn't have a radius to speak of.
Yep, so the size is negligible. That's why it can't spin, because it doesn't have a radius to speak of. But the point is to question this idea when I say structureless point particle. But when I say point, I mean 0 size. But if I take the most state-of-the-art electron detector, and it has a particular pixel size, which if I buy my fanciest, most expensive camera, it has the smallest pixel size possible. And I say when I catch my electrons, they will fill this particular pixel. And that might be, 10 to the minus 6 of a metre pixel. You might do particular experiments, scattering experiments, where you can be sensitive to sizes that are much smaller. You can have indirect experimental tests of the size of an electron. But here's the point. All our current experiments which attempt to see some finite spatial extent to the electron have failed. Does that mean that the electron has no finite spatial extent? You're shaking your head, this is good. What does it mean when all our experiments to date, which attempt to see the spatial extent of the electron, have failed to come up with a non-zero answer?
It means that we can't resolve it properly if it is finite.
Beautiful. It means that we can't resolve it properly if it is finite. Does someone want to run with this? We can't resolve it properly if it is finite. Do you want to run with your own answer? Because I like this.
Well, the smaller we get, I think I remember something, the more uncertain we become, something like that. So the more we zoom in on the position, the more we lose the momentum. So there's a point where you can't resolve anymore.
Yes. For
us at the moment.
Absolutely. There's a point at which we can't resolve any more at the moment. I'm actually going to take an aside to explore this particular point. Here's a structureless point particle, has 0 size. I'm trying to have my electron, and I'm trying to look at that single electron from a progressively smaller and smaller dimension of space. So here we have a certain dimension of space, delta x. And we have a position momentum uncertainty principle. And whether you have h bar or h bar on 2, depends on your definition of uncertainty. I don't really care about the factors of 2 here. 2 is approximately equal to 1, and please don't quote me on that. In the context of a back-of-the-envelope calculation, the point is that the smaller delta x is, the bigger delta p will be. Yep. The smaller delta x is, the more uncertain the momentum will be. Eventually, you'll have enough momentum to create an electron-positron pair, right? You know the most famous equation in all physics, which says that energy and mass are the same thing. If delta x is sufficiently small, then the fluctuation in the momentum can become sufficiently large that you no longer have one electron. That one electron might morph into 2 electrons and a positron. So the very concept of an isolated point particle becomes meaningless beyond a certain spatial extent. You can actually calculate this, and this minimum for delta x, smaller than which the very concept of a point particle becomes ill-defined, is called the Compton wavelength. And you can calculate it, and it's the following, and it's roughly 10 to the minus 12 of a metre, which is roughly 1/100th of the size of an atom. So a point here is that the very concept of a point particle is ultimately problematic. Whether you give arguments based on the uncertainty principle or you just make the pragmatic point, just because no experiment can detect the size of the electron doesn't mean it's 0 size. It just means its size has a certain upper bound. It means that its size, we're not sensitive to it. That could be because it has no spatial extent, or it could be because its spatial extent is smaller than any experiment can currently resolve. How does that ambiguity affect the argument? An electron is a structureless point particle, and therefore spin has no quantum analogue, no classical analogue. How does that ambiguity affect that conclusion, if at all?
It does have size, it does have a classical analogue.
Yeah, so if it does have size, it may have a classical analogue. Yep. So what we're doing here is we're looking at current states of knowledge and just trying to push things as far as we can, and to ask questions which reveal the fact that there's many things that we don't know, right? So very, very quickly you can come to frontiers of knowledge if you ask the right questions. And again, I want to emphasise this idea that any chain of argument that you're given, whether it's a mathematics argument, a physics argument, shine the microscope of your mind on it and question every single link. When you look hard enough, you'll often find problems at the frontier of knowledge. Or you might just find that the chain of argument is wrong. All right, I'll stop there and move on to some more pragmatic things. In fact, let me ask one more question. I gave this a name. We called it the magnetic quantum number. The magnetic quantum number, I'll denote the word number by a hash. The magnetic quantum number in the general theory of angular momentum, and in when you're considering the specific theory of angular momentum, the analogue of those two generalised equations was that L squared acts on a spherical harmonic, which is a function of theta and phi, to give the eigenvalue times the spherical harmonic back again. Now, I don't care about that equation, I care about the next one, which is that the z component of angular momentum acts on our generalised spherical harmonic to give what I call the magnetic quantum number m times the spherical harmonic back again. So I just want to ask the question. I didn't tell you. I mean, I said, let's decree that this is called the magnetic quantum number. So you could just view that as a term that you believe, swallow, and use. But let's ask the question. You know, we're talking about orbital angular momentum. And I've introduced this term magnetic. Why am I going to call this the magnetic quantum number? What is the link between magnets and orbital angular momentum?
Is that just where it was first observed with the experiment that you were talking about, where the electrons diverge?
So the question is that where it was first observed? The answer is yes, it was. That this idea of magnetic quantum number was first observed in the context of Stern-Gerlach experiment. Even though that statement's correct, can I find another answer? I mean, this is absolutely correct, but can I find another answer for this link between, where this name comes from?
Because you have a moving charge, don't you create a magnetic field?
Yep. So since you have a moving charge, don't you create a magnetic field? Can someone run with this observation?
Well, particles with different spin, they're going to induce different magnetic fields that act differently when added vectorially to the field you apply, so that's why they'll diverge.
Yeah. So this is good and correct, but I want a simpler answer. This is the charge which is moving, but we're talking about orbital angular momentum. We're talking about charges that do this. So here's a charge, smeared out through space, which is doing this. So moving charges absolutely create magnetic fields. If I have a charge and I do this, I create a magnetic field. I mean, when you have charges going around in circles, that creates a magnetic field. What does that make you think of? What? Solenoids? Beautiful. It makes you think of solenoids, because a solenoid is charges doing this. Charges that have orbital angular momentum create magnetic fields. Now in a solenoid, you have the current going through this loop, but when you have the current loop, an electron which is swirling, for example, an electron that's swirling around a nucleus in a hydrogen atom, then orbital angular momentum of charges create magnets, and those magnets can have particular orientations, which is precisely what the Stern-Gerlach experiment is doing. So it's the connection between orbital angular momentum for charges in motion, charges in rotational motion, and the link with magnetism, an example of which is the Stern-Gerlach experiment, an example of which is the solenoid, an example of which is the sort of minimal solenoid, which is the current loop. So this also makes the point that when we're studying orbital angular momentum, we're also studying the quantum theory of magnetism, right? When you have electrons, charges swirling around atoms or nuclei, or in molecules or in crystals, then you're talking about little current loops, you're talking about solenoids, you're talking about a quantum theory of magnetism. All right, let's actually do some calculations that will help you answer particular technical quantum questions. So let's look at exercise 19. Now, I don't actually want to derive exercise 19. I just want to recall some of the results because we need them. So you have two linear operators, A and B, and the commutator of these linear operators by definition is AB minus BA. The exercise 19 lists four consequences of this definition. So what we're doing here is deriving four results from commutator algebra. Because we're going to be using them when we do our general theory of angular momentum. So let me just recall three of those results, the three results that we need. The first is that if you have a commutator of linear operators A and B, and if you were to flick them around, then you pick up a minus sign. The second result is that if you have the commutator of A with B plus C, here A, B and C are linear operators. And this gives two commutators, the first of which is AB and the second of which is AC. The third result is the following. How about the commutator of A with BC? By the way, is this called, there's a name for this, I've forgotten what it is. Distributive, associative, distributive. Yeah, beautiful. This is a distributive law for our commutators. This is about a certain asymmetry and anti-symmetry of commutators. And here's a third result. The fourth one that's given, we don't need. By the way, the fourth one, the fourth one we don't need. The fourth one is closely linked to the idea of the Einstein field equations, but that's a story for another day. Here we have this commutator. I want to give you a mnemonic. As always, I try to work frogs into any quantum lecture I can. So you can derive the following result using this definition, but you can remember it like this by thinking of frogs. So we think of this B and C as a frog, and the B frog could hop to the left. And if the B frog hops to the left, you get this. Alternatively, you could have the C frog hopping to the right. And if the C frog were to hop to the right, then you get A commutator B with the C frog on the right. And that's a silly way to remember it, but it's quicker than deriving it. So I'm just reminding you of these three results of commutator algebra. So what we want to do now is to do exercises 57 and 58. Now the context here is the general theory of angular momentum, and all we have to work with in the general theory of angular momentum is what is on that top board. Yep. So all you have is this, your three Hermitian operators Jx and Jy and Jz, which obey this Lie algebra. That and nothing else. So the first thing we want to deduce is exercise 57, which is a statement that J squared has a zero commutator with Jx and Jy and Jz. And I'm just going to do one example of this, which is to show that the commutator of J squared with Jx vanishes, because the commutator of J squared with Jy or Jz will be analogous. So as a first step, what is a good first step? I'm stuck at the very beginning. I want to calculate this thing. What's the first thing I could do?
Split up J squared into its components.
So split up J squared into its components. Can someone else tell me the next thing to do? Hint, one of these might be relevant. Is this one relevant? No? Beautiful. This one? Yep, beautiful. So let's use this distributive law. Now whether you have a sum of operators in the second slot or the sum of operators in the first slot, the distributive law still works. You can prove that to yourself. So this is going to give us three commutators. The first one, Jx squared with Jx. The second one, Jy squared with Jx. And the third one is Jz squared with Jx. Now, I don't like that first term. I want to cross it off. In fact, I will. Why can I cross this off on inspection?
Because you've just ended up with Jx cubed minus Jx cubed.
Beautiful. So the answer is I can cross this off on inspection because I'll just end up with Jx cubed minus Jx cubed, which vanishes. That's good. Now I want to manipulate this one. what would you recommend that I do with this term here? Should I apply rules 1, 2 or 3, or none of the above? Third one. So let's apply the third one. And by the way, if you think of that frog hopping analogy, whether it's A, B, C, or A, B, C, that frog hopping analogy will still give you the right answer. Yeah. So this is JY twice, and the first JY could hop out the front, leaving a JY, JX, or the second JY here could hop out the right-hand side. Similarly for the third term. Now, please tell me if I screw up, because if I screw up, it's not going to work. JZ can hop out the left, or the second JZ here can hop out the right. I'm stuck again. Can someone help me? So use the relations in the middle. Remember how little we have, right? We've got the definition of a commutator. We have some rules of commutator algebra. But ultimately, everything's going to flow from this. So one of the things that you can use is the commutator relations. And again, remember that those three equations of the Lie algebra are related via cyclic permutation. So any two distinct operators, let's say Jx and Jy, you're going to get IH cross times the other one. Is it a plus or a minus? Well, if it's X, Y, Z, cyclic order, then it'll be a plus IH cross. If it's around the other way, you'll have a negative. So let's do that. JY, here we have JY, JX. It's going to be IH cross JZ. The other one, Y and X have been used. Is it cyclic order? No. Y and X is not in cyclic order, hence you get a negative sign. Yep. Here we have IH cross times the other one, JZ. Is it cyclic order? No, therefore it's a minus. And we have our JY. And similarly for the remaining terms. So here we have JZ. This is in cyclic order. Z and X will give IH cross with a plus times JY. And lastly, Z, X will give IH cross JY, and the JZ hangs on for the ride. Now, I kept asking you to look for errors and holes in the argument. Have I got that right? And if not, where have I screwed up?
Can the negative go on the left for the first one?
Yeah.
Can you take the negative out?
Can we take the negative out? Absolutely. So you want to factor this, pull this negative out the front? Yep, absolutely. So all numbers are like nomads, right? I know that order matters in quantum mechanics, but numbers can go anywhere. Numbers are nomads, so you could factor out the negative, you could factor out an IH cross. Let me actually factor out an IH cross from everything. So I'll have JZ, JY. Which is this term here. Minus JZ, JY. In fact, these cancel. And these cancel. And so the whole thing vanishes. Excellent. So this all equals naught, which is what we wanted to prove. I'm very glad that worked. Now we want to crank it up a notch and do exercise 58, and we'll see how far we get through this. Exercise 58 is 3 results which follow from what we've written regarding these definitions, You can make use of these consequences of the definition of a commutator. Exercise 58 gives 3 results. The first of which, all of which are used in the general theory of angular momentum. So the first is to calculate this commutator. And I'll just remind you that J plus minus, J plus is Jx plus Ijy, and J minus is Jx minus Ijy. So the first thing is to show that this commutator equals naught. And the way to do this would be to, let me actually leave that as is. I've got a Jx, I've got a Jy. I'd now use, what would I do next?
Distributive formula?
Distributive, yep. I'm going to keep this J squared for reasons that will become clear in a second. So here's the Jx, the plus or minus I comes out the front, J squared, comma, Jy. But we know that J squared commutes with Jx, J squared commutes with Jy, so this equals naught, which makes us happy because that's what we wanted to prove. So this is the first thing that we want to prove in exercise 58. The second's a bit trickier. We want to consider J plus times J minus and deduce what this equals. In fact, we want to show that this equals J squared plus or minus H bar Jz minus Jz squared. This is what we want to prove. So that's one of the things we want to prove. The second equation we want to prove is that J minus times J plus equals J squared plus or minus H bar Jz minus Jz squared. So there's 2 equations here. And this is what we want to prove. So we begin with the left-hand side. What's the next step?
Expand it in terms of Jx and Jy.
So expand it in terms of Jx and Jy. So J plus or minus will be Jx plus or minus Ijy, and J minus plus will be Jx minus or plus Ijy. Now there's a difference between plus and minus plus. You can either read the upper signs or the lower signs. Yep. Now, even I know what to do next. I'm going to expand those brackets. So let's do that. But before I go on, I do the classic thing, right? I know the answer, and I know that the answer has a Jz in it. But this is classic trial and error logic. I want a Jz squared in there. There's no Jz's here. Maybe I could pull some fancy commutators to introduce it, but you know, a J x and a Jy at the very best would become a Jz, right? A Jx and a Jy at the very best would become a Jz. I want a Jz squared, so if I want it, let me put in what I want and then undo the damage, right? So I'm just putting in by hand a term that thank you. So I need a square here. So I put in, thank you, I put in by hand a term that I want using rough logic that's going to say that this is never going to give me a Jz squared. So I'm going to put it in by hand and undo the damage. All right. So we've done that. And now we continue. I'll just expand the brackets. I'll get Jx squared minus or plus I, Jx, Jy, always keep the order correct, plus or minus I, Jy, Jx, plus or minus times minus or plus is a negative, because plus times minus is minus and minus times plus is minus. We have an I squared, which is -1, that turns it into a plus, and then Jy squared. Plus Jz squared minus Jz squared. I want a j squared. Here it is, jx squared, jy squared, and jz squared. All those terms funnel into j squared. That's good. I wanted a minus jz squared. I've got it, because I put it in by hand. And in retrospect, this is just a jx squared plus jy squared. What's left, unfortunately I've run out of time. When you calculate what's left, you'll get something times the commutator of jx with jy, which turns into a jz, and that will give you a plus or minus h cross jz, which is what we want to prove. This is second of 3 elements of the toolkit in exercise 58. I'll stop there, and I'll see you all next week. Thank you. Again, happy to answer questions after class for as long as you want.